Bismillahirrahmanirrahim. Previously we've talked about histograms, and this is one of the examples that we gave. If you recall, a histogram is a bar graph like this, a plot, where on the x-axis is a range or whatever it is that you're talking about. In this case, the number of rooms available, and on the y-axis is the frequency in whichever form that is to be displayed. So this was an example of a bar graph. So the bar graphs have ranges on one side and frequency on the other side. And we have suggested there's different types of histograms, and this was a probability histogram in which a particular outcome is graphed in terms of its probability. Here, the probability of getting 4 rooms, the probability of getting 5 rooms, which is a little less, and probability of 3 rooms, which is a little less. And if you also recall from that conversation, the sum of all of these probabilities, of course, the all possible outcome would have to add up to 1. So the sum of all probabilities add up to 1. So this was an example of a probability histogram. I had also given at that time another example, the probability of rolling a certain number when 2 dice are rolled. So here are 2 dice and the possible outcomes of each dice and the sum of these possible outcomes. And from this we had also generated another probability histogram. So the lowest sum that can be gotten from rolling 2 dice was 2, of course, and the highest sum was 12. And between this range of different outcomes, so this was the range of outcomes, and we had suggested that 7 was the most likely outcome because there were many different ways of getting 7 than any other combination numbers. And this was the probability curve of the sum of numbers for 2 dice. So this was again an example of a probability curve. Here's another. Here's the probability curve for this particular example. Now, if you notice in these examples, all of these curves had a particular shape, and they had kind of like a bell curve shaped over here, which is what the object of our study today, the bell-shaped curve or the normal curve. And you will also notice that the greater the number of discrete items in the range, okay, the more the bell-shaped curve looks like, the more bellish, so to speak, the bell-shaped curve looks like. See here, in this case, this which I found on the internet, and number of employees of a cereal factory, the numbers of years that they work, so the range includes from 1 year to 20 years, and the frequency of those employees. This was also a bell curve. And here, the possible outcomes were even greater, and you will also notice that the shape of the bell curve was more looking like a true bell curve. So this is a frequency histogram. Here's another example in real life. The weight of patients in this particular study and the count. This is a frequency histogram, and notice that it also resembles a bell curve. The point of these exercises is that there are many circumstances in life where outcomes, when you graph those outcomes in histograms, they appear to be like bell curves. They don't have to be. There are many situations where they are not, but there are many times where there are. So again, here's a probability, a different scenario. And here's another example. The more discrete outcomes there are, the more it resembles a bell curve. In other words, the skinnier these rectangles are, the more bell curve shape the graph takes if the distribution is in this manner. This leads to the ultimate bell curve. Now, this ultimate bell curve, known as the standard distribution, standard normal distribution, is a hypothetical situation. It is a model. In other words, this is an intellectual exercise. All right. In this case, the number of the ranges goes from negative infinity to positive infinity outcomes. So in other words, this curve technically never ever ends. So the x-axis is kind of like the asymptote. So this is a model. It's a intellectual exercise where every discrete item, there are infinite number of discrete items in the range. Okay, but this bell curve is also a probability curve. In other words, if you were to take up the area under the curve, right, it's each individual rectangle thing, the area under the curve, is the probability of all possibilities. When you add up all the possibility, and because it's a probability histogram, this would be area under the curve would be 1. Now, as I've suggested, many life situations resemble the bell curve. So if we study the bell curve, then we can understand much of the data in real life as well. Although the standard normal distribution that you see in front of you is a theoretical construct, an exercise in intellectual imagination in some way, but if you study this ideal model, then you can learn a lot from the behavior of real life situations and apply and extrapolate the knowledge that you have learned from this model into real life situations. So what I'd like to do today, inshallah, is to study this model and actually reproduce this exact same picture diagram and show to you how at least I do it, and you should be able to actually reproduce this very picture, inshallah, at the conclusion of our discussion here. So our goal is to learn this and be able to draw this by ourselves if we had to, okay? Inshallah. All right. So the topic of the day is normal distribution curve. As I have suggested, this is also known as the normal model. Now, this particular term, it goes by various different names, but this particular one I like because of the implication that this is a model. Okay. All right. So now it's actually quite important to be able to draw this. Okay, and if you take some steps. Proper steps in drawing it, it's very, very helpful. So normal model, okay? So, in fact, I would encourage you that you should draw it sufficient number of times that you feel quite comfortable with it. So, I have a hard time drawing like the bell of the bell curve myself in one stroke, but let's give it a try. So, it is symmetrical, supposed to be symmetrical, the ideal curve. The best we can. Let's make it like this. Now it's supposed to go on forever. Perhaps we could do a little bit better here, don't you think? All right, that will have to do perhaps. All right, so this is supposed to go on forever, but I'm going to kind of like cut it off over here, just for convenience. Okay. So now again, in this model over here. Right in the middle of here is the middle of the curve. The curve is symmetrical, okay? And if this was a real life situation, whatever you would apply to this, on this axis would be the range, correct? This would be the range of values, okay? So if you were talking, for example, of patient weights, this would be the skinniest patient, the smallest patient, and this would be the patient with the greatest weight. If you were talking about the rainfall in a certain area, this would be the smallest amount of rainfall, and this would be the largest amount of rainfall. The smallest amount of rainfall, the largest amount of rainfall, and the smallest amount of weight in our example to the largest weight in our example. So that's the range of values. Now, because this is a very nice and neat symmetrical ideal model of an ideal world, smack in the middle of this would be the mean. Okay, smack in the middle of this would be the mean. Okay, so this symbol is used variously. Let's put it over here. Okay, this is going to be the mean, okay, which is like the average. Now, different textbooks give different alphabet soup for this. and this is also written as mu, okay, as in mu, okay, or I've learned to combine these two, and m for mean, and you can put a little mu there to remind yourself mu. So there are various different symbols that you can use for this, okay. Now there's the normal model behavior, okay, and the behavior of normal of data that behaves as a normal model, okay, is governed by a rule, and this rule is called the empirical rule. And this is like super duper massively important rule, okay. Empirical rule. This is how many times information on big studies on many medications are listed, ACT, SAT scores are listed, and whatever in large data is listed in this fashion. So it really helps to know the empirical rule. Empirical rule has to do with the distribution of data in this bell curve. Now we already know that since the bell curve is symmetrical, half of the data will be on this side, and the half of the data will be on this side, right? It's perfectly symmetrical, okay? So half of the data will be on this side, and half of the data would be on this side. And also recall that this is a probability distribution. This is a probability distribution. On this side would be probability, okay? Now, also, this is a continuous data with infinite number of data points. So you can't just apply real situations to this, but we have some governing rules. Okay, but the empirical rule which we're talking about is this. The massively important rule, empirical. Empirical rule says, okay, that if you take the mean, okay, and if you go one standard deviation away from the mean, and then 2 standard deviation from the mean, and then you have captured a certain number of data, okay. Now to understand that, okay, we're going to have to do the following exercise, okay. So our job here first is to understand the empirical rule. Now the mantra of the empirical rule is 68%, okay. If you want to like memorize this, okay, empirical rule is 68, 95, okay, and 99.7%. Okay, we're going to explain what this really means. I basically remember 68 and 95. Okay, so empirical rule states basically that one standard deviation from the mean, you'll find 68% of the data in that duration. So this is how you graph the standard curve. So this is what we need to learn. Okay, to make the picture that we wanted to make, the whole complicated normal picture, okay, you first draw this bell-shaped curve, and then you draw the mean right in the smack in the middle of it, right? And then I gotta go erase this because I want to do it from the beginning. Okay, so we want to draw the complicated picture. So we've drawn this, right? So what you do is, okay, you go in there and you kind of like cut off this part of the graph. Okay, just cut it off. All right, and then over here it's going to be a little bit, you kind of cut off the tails of the graph. All right, just cut them off. Okay, all right, so we cut off these tails. Okay, now all of this data right here, okay, that's going to be 2.5% of the data. It's going to be 2.5% of the data. Okay, and then what you do, okay, is what remains over here, whatever remains over here, make a little, cut it in half. So this from here to here, you cut that in half, and from here to here, you cut that in half. Okay, all right, once you do that, you just draw a line straight up over here, and you draw a line straight up over here. It's not real. All right, we've done that, and I just like to just connect them in a box like this. Okay, and then let's use, I don't know, let's just use Let's use purple. That looks good. And then you take from over here, draw a bigger line. It's like a goal post, a bigger line over here. Okay, you can connect them if you want it like this. All right, so okay, this is that's connected like that. Okay, so all right, we got that. Perfection is the enemy of good. Okay, so here it is. Now what are these boxes? Okay, now. So from here to here, okay, is one standard deviation, okay. And from here to here is two standard deviation, okay. So you take the mean, which is the middle of the graph here, and in a normal curve, mean, median, move all the same. They're over here. So if you move one standard deviation from the mean right here, and if you move one standard deviation, it means you get this. So this is one standard deviation from each side. And from the mean, this would be two standard deviation away, and this would be two standard deviation away. Okay? Now, the symbol for standard deviation, so we got the mean over here, right? So we got the mean, all right? So the symbol for standard deviation, okay, is this. Okay, this is sigma. This is Greek letter sigma, and that stands for standard deviation. Okay, different books use different things. Sometimes I just like to call it standard deviation, which kind of looks like sigma anyways. Okay, so this is going to be mean plus one standard deviation. Okay, and this is going to be mean plus two standard deviation, and this is going to be mean minus one standard deviation, and it's going to be mean minus two standard deviation. Now you can go farther as another standard deviation. Okay, now previously we talked about standard deviation. Standard deviation is the average distance that a particular number is from the mean. Okay, so okay, from here to here is one standard deviation, and from here to here is another standard deviation. So this point here is two standard deviation away, and this point here is one standard deviation away, right? And the other way is from here to here is one standard deviation, and from here to here is another standard deviation. Okay. Now the empirical rule that we talked about says, okay, here's the empirical rule. Okay, if you recall, that's 68%, 95%, and 99.7%. The empirical rule says, okay, that 68% of the data is within one standard deviation of the mean, right here. One standard deviation here, one standard deviation here. Okay? In other words, okay, if you were to take all of this, okay, that is 68% of the data. 68% of the data is over there. Okay? That's what that means. Okay. Now, and then the 95 says that 95% of the data is within two standard deviations. So here's one standard deviation, here's two standard deviation. Okay, that's 95% of the data. Okay, so that's what the empirical rule means. And three standard deviation. If you were to go out another standard deviation, you would get over here. You would capture 99.7% of the data. So if you want to know the empirical rule, okay, what you have to understand is this. Okay, the empirical rule says that in one standard deviation away, there's 68% of the data. Okay, I can write that 68% from here to here. Okay, and in two standard deviation, there is 95% of the data. Okay, that's the empirical rule. So if you want to know what empirical rule is, it is this. Okay, in one standard deviation, you have 68% of the data, and in 2 standard deviation you have 95% of the data all together. Okay? Alright, so we got that. Okay, that you must understand. Okay, so now there are other things here. Okay, we got this. Okay, now if you were to look at this, okay, so mean is smack in the middle of the whole data set, right? Okay, so 50% of the data is on this side and 50% of the data is on this side. So because this graph is symmetrical. Okay, if 68% of the data is included within the standard deviation, that means 34%, half of 68%, is over here, and the other 34% is over here. Okay, so 34% data is in this like pie, so to speak, and the other 34% is in this pie. Okay, and then if you subtract 95 minus 68% and then divide that into 2 parts, okay, and then you'll see that this is going to be 13.5% of the data, and this is another 13.5% of the data. So 68%, that gives you 2 half, 34%. Subtract that from 95%, right? And then divide that 2, you realize that these are 35%. Now look, so now we have all of these percentages. Now, okay, so now there are 2 other things that we have to learn. One is a concept called, now there are 2 other things that we need to add to this graph, okay? But before I add that, I just want to re-emphasize what you're doing here is you are basically chopping off this normal distribution curve based on standard deviation. So from each one of these, from here to here is 1 standard deviation, from here to here is 1 standard deviation, from here to here is 1 standard deviation, from here to here is 1 standard deviation. We only went 2 standard deviation, or you could go another standard deviation. That would be 3 standard deviation on each side of the mean. That would capture 99.7% of the data. Okay, so that's what we're doing. We're chopping off the normal distribution in each piece being 1 standard deviation in width. Now, as I said, we have 2 other things that we need to add to this graph. Okay, and I'm going to put them over here. All right, and these are very important. All right, kind of like let's put it like this. Okay, and the first is percentile. And this is very important because a lot of test scores are given in percentile. Okay, and I'm writing it on both sides just because the graph is symmetrical and it's just easy reference. Okay, so percentile, and the last thing is the something called the z score. Okay, now let's talk about the percentile. Now let's imagine that there was a little ant. Okay, so the little ant was walking this way over here, right, going this way. So imagine the little ant going this way. By the time it reached this marker over here, okay, by the time it reaches over here, it would have captured 2.5% of the data, right? Because 2.5% of data is this way. Okay, so this part of the graph, okay, this part of the graph, okay, this part of the graph contains 2.5%, okay, of the data. So from the time it gets to here, there's 2.5% of the data. Then it keeps marching over here, and then it reaches to this point, right? Now this part of the data then will contain 2.5 plus 13.5% of the data. Okay, so so let me get rid of that. So from here to here, okay, all of this stuff contains 13.5 plus 2.5. Okay, that's 16% of the data. Okay, So we write this as 16%, corresponding to this point right here. And of course, by the time you reach in the middle, you have 50% of the data. Okay, we can just write it over here. Okay, and I'm just going to write that in red because it's smack in the middle. It's 50% of the data. Okay, and then you keep moving on here. And by the time the little ant gets over here, this would be 50% plus this chunk of data. So this is 84% of data. In other words, 84% of the data is from here on. So all of this is 84% of the data under the curve, of course. Okay, so that's 84% of the data. And then if you go capture another all of that, okay, that is going to be 84 plus another 13.5%. That's 90. This point right here is 97.5% of the data. In other words, okay, each of these little landmarks, if they were like little posts, you know, road posts for the little ant, marks how far it has traveled. By the time it gets here, there's 2.5% of the data here. By the time it's over here, it has already passed 16% of the data. By the time it gets to the middle, it has passed 50% of data. By the time it gets here, it has passed 84% of the data. By the time it gets here, 2 standard deviation from the mean, it has passed 97.5% of the data. Okay, so the percentiles tells you how much of the data is below that particular point. Okay, so percentile at this point means, okay, this is 84%, means 84% of the data is on this side of this line right here. 84% is this way. Okay, that's what percentile means. If somebody's score is 84%, 84 percentile, that means 84% of the people are below them. Okay, if somebody's score was 90th percentile on a test, that means that 90% of the other students did not do as good as they did. Okay, so that's what percentile means. It's the data below that point. Okay, so that is percentile. Now notice how you get that. You start off with 2.5, you add the 13, and you add the 34, and you add the 34, and keep adding up to get these percentiles. Okay, so now the z-score is basically a score that's given in reference to the mean. Okay, so the mean is a z-score of 0. Okay, if somebody's standing at a mean, their z-score is 0. Okay, now 1 standard deviation away from the mean, their z-score is 1. In other words, from here to here, we said 1 standard deviation, right? That's a z-score of 1. Okay, now if you move another standard deviation, that's 1 plus 1, their z-score is 2. And going this way, if you move 1 standard deviation away, z-score is -1. And if you move 2 standard deviation away, z-score is -2. Okay, there's also a z-score of 3 and -3, right? Another standard deviation, which we didn't do here. Okay, now look what we have gathered here so far. Now, this is the mean. This value is going to be 1 standard deviation from the mean. This value is going to be 2 standard deviation from the mean. 1 standard deviation below the mean, 2 standard deviation below the mean. Okay, and then we suggested the empirical rule. The empirical rule tells us how much of the data is under the curve, how much of the data is in the curve relative to standard deviation. 68% of data is within 1 standard deviation of the mean. Okay, and then 95% of the data is 2 standard deviation within the mean. Okay, and 99.7% of the data is 3 standard deviation from within the mean, like this. Okay, now that's the empirical rule. And then the percentiles are calculated like this. Now this, all of everything that you see in front of you, this applies to any situation that resembles the normal distribution, normal model. In real life, as I said, it's very difficult to get perfect normal curves, but anytime a normal curve type behavior is observed, you can apply these rules. In other words, if you know the mean for particular data, then you can say that 1 standard deviation from that mean, you'll capture 68% of the data. If you wanted to apply this to a real life situation, you would put real life numbers over here. Okay, and from starting the x values, whatever the x values are from the ranges, you can put over there. But everything that you see here is a theoretical model that can be applied to every situation that can be modeled by the normal model. Okay, so let me as some mental exercises so you understand this, ask you the following. Okay, now if one were to ask you what percentage of the data lies below the mean, so what percent of data is below the mean? Okay, that's pretty easy. That's because the mean is right in the smack, so the answer is 50%. So 50% of the data is below the mean. Okay, now what percent of the data is below 2 standard deviation from the mean? So if you have the mean and if you take 2 standard deviation from it, what percent of the data is below that? Well, 2.5% of the data is below that, right? Okay, so this is the general basic outline of the normal model or the normal distribution curve. Okay, after a brief pause, I'm going to elaborate on this and we're going to do some examples to further understand the normal model. Okay, so until then, Assalatu wassalamu ala rasulillah, alhamdulillahi rabbil alamin, assalamu alaikum.